If an object sliding on a table initially with a kinetic energy 1/2 mv squared, does that energy get converted into gravitational energy? That might seem like a bit of a weird question there, but in the last example, we saw how it is correct to describe free fall in terms of gravitational energy converting into kinetic energy. If you did the opposite of that process, like if I took an object and simply tossed it upward, it would make sense to say that that object, right after I tossed it, maybe started with some amount of kinetic energy, and then when it gets to the very highest point that it gets to, then all that kinetic energy got converted into gravitational energy, and all of that makes sense. So far, again, we've been talking about transformation of energy into from kinetic to gravitational, or the other way around. But is that what always happens? So here we're talking about an object sliding on a table, right? And what's different conceptually about that, right? So let's say here's, like, I don't know, some box-like object or whatever, and it's moving with a velocity v. And if we compare that conceptually to say, like, hey, if I, let's say, had tossed a box-like object up with an initial velocity v, and we know that, like, in that sense, if I looked at, like, hey, let's say this is the maximum height it gets to right here. In this case, I could definitely say, okay, what's the deal with the initial? It has kinetic energy, and I'm just going to say Ke here to abbreviate that. And if I tossed it upward, it makes sense that in the final state, it maybe just has some gravitational energy. I'm just going to say Ge here. The object slowed down. So why would, like, if what happens when the object's sliding on a table? Well, it eventually winds up at rest some later point, right? So here v is equal to 0. In that sense, if I were to look at this one, I could say, okay, initial, right, definitely kinetic energy here. The question we're really being asked then is, what would it make sense if I also said, like I did in this situation, that gravitational energy is the final form of energy here because it lost all its kinetic energy? Well, okay, what's one key difference? If you did this, would you expect the object to come to a stop and then kind of fall back to you? No, that would never happen, right? Whereas here, I mean, I've kind of decided on an initial and maybe a somewhat arbitrary final point, but if I did nothing else and I just kept time rolling, this thing would fall back down. If my hand were down here, I could catch it, right? That's totally not going to happen here. And these are both mechanical energy forms, and it turns out the fact that it kind of reverses the way I just described is kind of a feature of transformations between different types of mechanical energy forms. But what happens here in going to the final state here is there's friction happening, and that produces heat. And it turns out from an energy perspective, that produces thermal energy. Maybe I'll put Te here for thermal energy. I don't know if that'll be confusing to say it that way. Anyways, but one of the differences between thermal energies and the mechanical energy forms, it turns out thermal energy is not mechanical energy. In fact, generally speaking, when we're looking at, there's kind of two broader categories, you could say, of energy. There's mechanical energy and there's thermal energy, although thermal energy has less variation in terms of how it shows up. It generally always means the object is getting warmer. Its temperature increases or something around there. Maybe it's also the surface of the table that the temperature increases. But the thing about this energy is it won't as easily return back to a mechanical energy form. So there is something different going on. So to maybe finally, in a less long-winded way, answer this question, does the energy get converted into gravitational energy? No, it does not. Another way I could have looked at this, I could have simply said, well, gravitational energy is associated with height. This one never went up in height. This example, the object did. So that's another way of seeing it. Let's see what the answer says. It says no. Historically, physicists weren't sure what happened to the energy in this type of case. So as I've been discussing here, one of the issues is that the object won't naturally return back. Like if I toss an object up, what goes up must come down, right? Unless something stops it, I guess. But, it would come back down, and if there's no drag forces, it wouldn't have really lost any energy. But if I slide something across a table, it's not going to spontaneously return to me with the same amount of energy that I gave it to begin with. And that was actually very confusing for physicists. It made it troublesome, hard for them to kind of figure out how to develop correct definitions for energy that would actually work to describe reality. And then it was, actually this is misspelled here, it's James Prescott Joule, not Perscott Joule, so make sure not to write it that way in your notes, showed in 1847 that mechanical forms of energy like kinetic and gravitational energies can be converted into a corresponding amount of thermal energy. This is generally is what happens in systems where there is friction or other drag forces. So he did some really delicate, you could say, difficult to do actually in his time, experiments that quantitatively showed that the temperature change associated with a particular amount of thermal energy produced because of some loss of mechanical energy was predictable and made sense. And so that's what convinced other physicists that maybe it isn't just that energy magically disappears in a situation like this, it's simply turning into a different type.